In this video, I will talk about regression inference in Stata. Before you watch this video, please make sure that you have watched my other video called Regression Inference. So this is basically how to do hypothesis tests in Stata. So let's go ahead and get started. I have opened up here the program and I have already executed it by highlighting everything and clicking on do. So you can download this program and download the data file wage1.dta and specify where the data is located, and then you can run the program. So what we will do in this Stata program, we will talk about the Shapiro-Wilk test for normality, the t-test for coefficient significance, the f-tests for either single coefficient significance, joint coefficient significance, or overall significance of the regression. And then we will talk about Lagrange multiplier chi-square test for coefficient significance. So the first analysis that we're doing here is the Shapiro-Wilk test for normality. So we will read in data on wages, and then we would draw the histogram of a variable using histogram of wage, and then we would draw a histogram of log wage. So let me just quickly show you these histograms. I already ran the program, so here are the histograms. So if we look at the first histogram of wage and the second histogram of log of wage, one thing we're noticing here is that these are not bell-shaped curve and they are skewed curves. So these histograms are showing us a first indication that perhaps the distribution of these variables wage and log wage is probably not normal. So we can go ahead and formally test this with the Shapiro-Wilk test for normality, and that is S-Wilk, and then put the name of the variable. So we will test this for wage and log of wage. So here's the test statistic W, which is 0.8 for wage and 0.96 for log of wage. We are actually looking at the p-values of these tests, and because the p-values are less than 0.05, the variable is not normally distributed. Next, let's talk about a t-test for coefficient significance. So we would be reading the data for wages, and we would be running a regression of wage as the dependent variable. So we're using reg of wage as the dependent variable, education, experience, tenure, and female being independent variable. So this is the regression output that we will be getting. And so we would be now conducting t-tests for significance of coefficients. So let's look at the coefficient, say, of experience. So we want to know if this coefficient is significantly different from 0. So there are several things that we can do here. This is the coefficient. This is the standard error. So this t-statistic that we see here is calculated as the coefficient divided by the standard error equals the t-statistic. This is the p-value associated with this t-test that we see here. And basically this is the probability coming from the t-statistic to the closer rejection tail times 2. That's the area. And then we would be constructing this 95% confidence interval as the coefficient minus 1.96 times the standard error. That would be the lower bound here of the 95% confidence interval. And then the coefficient plus 1.96 times the standard error. This will be this value here. So let's go ahead, calculate everything, and then do the hypothesis testing. Okay, so as I said, first of all, we would be looking at the coefficient. And they're actually stored in the system as underscore b, and then in parentheses the variable name for which the coefficient applies. So here we would just call this coefficient underscore b for experience, and then we would be displaying this coefficient, and you can actually see that this is exactly the coefficient that we have listed here. So Stata has stored that. Same thing with the standard error. If you do underscore SE and then the name of the variable and then you display this, you will see that this standard error is exactly the same as the standard error in the regression output. So in order to calculate the t-statistic, we would be dividing the coefficient by the standard error. So we would be generating t-stat. So this was underscore b was the coefficient divided by the standard error, and we would be displaying the t-statistic, and notice that will be this number here. So here's the test statistic, and this is the number that I showed you there at 2.2. The degrees of freedom n minus k minus 1 is stored as e degrees of freedom for the residual underscore r. So this is already stored in Stata, and we would see that this is 521. So this degrees of freedom for residual, if you scroll up here, it's listed right here for the residual. So that's the same number as it is there. Moving on, we can display what the critical value is for the t-test with 5% significance level. And so to do that, we would be using the command invert t-tail. And here we will be giving it the degrees of freedom that we displayed above. And we are only leaving 0.025 in the tail because this is the 5% significance level split in two. And so if we are displaying this value, this would be exactly the 1.96. This will be the t-critical value with 5% significance level for a two-tailed test. So this is a very commonly used number, so I would recommend that you remember it. So now the first method says that if the test statistic is in the rejection region, then reject it now, and the coefficient would be significant. So we're looking at the t-statistic here of 2.2, and for a two-tailed test, it is definitely above the t-critical value. So it's in the rejection region, and therefore we reject the null hypothesis, and we find that the coefficient is significant. So method number 2 to test whether a coefficient is significant is to compare the p-value with the significance level. So here we would have a p-value for a two-tailed test, and this will be 2 times the t-tail. That's the command we're picking up the p-value from. Here are degrees of freedom and minus k minus 1, and we would be picking the absolute value of the t-statistic that we calculated above. So if we calculate the p-value using that way, we have a 0.029. So this is the p-value that we calculated by hand. If we scroll back up to the output, we would see that this is this p-value that is actually being listed in the output. So same thing. Okay, so here we have, this is the p-value. So if the p-value is less than the significance level, then reject it now and the coefficient is significant. So in this case, the p-value is less than 0.05, which is our significance level. So we again find that the coefficient is not significant. So this was a two-tailed test. So it says that the null hypothesis, the coefficient beta on experience equals 0 versus the coefficient is not equal to 0. We can also do an upper one-tailed test for a positive coefficient. So here we could have the beta of experience being positive for the alternative hypothesis and the opposite statement for the null. In this case, we would be displaying this would be t-tail, degrees of freedom, and the t-statistic. So this would be this number here. So because this is a p-value and it's less than 0.05, we find significant results. So what does that mean for significant results? We tested whether the coefficient is positive, and we find that yes, it is positive. The opposite test would be if we want to test if the coefficient of experience is negative, here versus the null hypothesis is that's not the case. So that would be a lower one-tailed test for a negative coefficient, and we would be displaying 1 minus the t-tail for the degrees of freedom and the t-statistic. So here we have a p-value that is very large, larger than 0.05, so we would conclude that the coefficient is not significantly negative. Well, we do have a positive coefficient. So these tests are the one-tailed tests are not very commonly used, whereas this two-tailed test is used a lot, and the p-value associated with that is in the regression output. So the third way to test hypothesis for coefficient significance is to calculate the confidence interval. So how do we do that? First of all, let's display the critical value at 5% significance level, and we would get this by calling inverse t-tail. We give the degrees of freedom, and we split the significance level into two because we have two-tailed test. And here is when we find that the critical value is being 1.96. So that's the t critical value with 5% significance level. So the lower bound at the 95% confidence interval is the coefficient underscore B for experience minus 1.96 is this critical value that we found here, times the standard error of the coefficient, and the upper bound at the 95% confidence level is the coefficient plus 1.96 times the standard error. So here we see that the interval is from 0.027 to 0.480 would be the upper bound. And so if we notice that these two numbers, they are actually the confidence interval that was provided to us with the regression output. So these are exactly the numbers that are listed here. We generated them by calculating them. Okay, so if the confidence interval does not contain 0, then reject the null and the coefficient is significant. And if I'm looking at the confidence interval, it definitely does not contain 0. So our coefficient is significant at the 5% significance level corresponding to the 95% confidence level. So now we can also calculate the critical value at the 10% significance level and the 90% confidence interval. So if we do critical value at 10%, we would be doing inverse t-tail, degrees of freedom, and we would just be leaving 5% in each tail now to get to the overall 10% significance level. And this number at the 10% is basically 1.65. That's why we use 1.65 for with 90% confidence interval. So here we would be calculating this confidence interval as the coefficient minus 1.65 times the standard error, or the coefficient plus 1.65 the standard error. So these are the 90% confidence interval for the coefficient. Okay, so notice that all three methods of comparing the uh, t-statistic with the critical value, the p-value with the significance level, and the confidence interval to 0 lead to the same conclusion. So we basically found that we have a significant coefficient, which means significantly different from 0, and this is the conclusion that we made using all three methods. So this was all doing a t-test for a significance of a single coefficient. So now let's start doing f-tests. F-tests. So the first f-test that we will do is for a single coefficient significance. So this is an alternative to a t-test, and it's done here just for completeness. But usually, if we have a single coefficient to test, we always use the t-test. We don't use the f-test. But let's use it for just learning purposes. So here we have h0 is the beta on experience equals 0. And this would lead to this unrestricted model. Uh, this would be the full model, the unrestricted model that includes all 4 variables. So we have regression of wage, education, experience, tenure, and female. This one, where we have the coefficient on experience restricted to 0, would result in that experience variable being dropped from the model. So now we have this restricted model that has different coefficients, of course, and different error. But we estimate the regression of wage on education, tenure, and female. Notice that experience is not included. So what we will do is generate the SSR for the restricted model, and this is where that SSR is stored. So this would be E of RSS, the residual sum of squared. So when this regression is estimated, we would be storing the sum of squared residual, which is this number here. Okay, so if we estimate the unrestricted model, we would be storing the SSR for the unrestricted model. So we would be calling it the SSR underscore unrestricted, and Q here would be the number of restrictions, which is 1 because we have one coefficient that we're testing, and then we're picking up the sum of square residuals for the unrestricted model as the same E of RSS. So this one would be picked up from the unrestricted model, which is this value right here. Okay, so now we're ready to calculate the F statistic here. So how we're going to calculate the F statistic is using the formula. That the F statistic is the sum of squared residual for the restricted and unrestricted model, the difference of them, divided by the sum of square residual for the unrestricted model. And these are the degrees of freedom that are correcting. So using all the stored values from above, we are calculating the F statistic and then we're displaying it. So if we look at the F statistic, that would be the number here. I'm sorry, that would be the F statistic would be the number here. It would be 4.82 for the F statistic. So now we can calculate the critical value, and we're doing this by using the inverse F tail. Q is again the degrees of freedom for the numerator, and then these are degrees of freedom for the denominator, and we leave a 0.05, which is the significance level, and we don't split it in two because an F-test is an upper one-tailed test. So if the S-stat is greater than the F critical value, we would reject the null and the coefficient is significant. So if we calculate the F critical value, this is a 3.85. And so now we need to compare the F statistic to the F critical value. And we see that the F statistic is higher. So therefore, we're rejecting the null and the coefficient is significant. Another way in which we can do an F-test is to display the p-value of the test. And so that would be done with F tail. And again, degrees of freedom for the numerator, denominator, and we put the F statistic here. So this would give you the p-value for the F-test, and that is the 0.029. So if this p-value is less than 0.05, we would reject the null and the coefficient would be significant. So notice one thing is that although this F statistic of 4.81 is very different than the T statistic we had above, the p-value is actually identical, is is the same as we have above on the t-test. So what I'm saying here is that if we go back all the way back to the first t-test that we've been doing, this is the t-statistic and it's completely different value, but the p-value of the tests are the same. So we would be getting the same conclusion about this coefficient significance with using a t-test or using an f-test. So continuing on, we have we can do an f-test for a coefficient significance using Stata command. So this is the easiest to just do it straightforward by just running a regression of all of the variables, and then we use the command test experience equals 0. And so here is test for experience equals 0. It gives you exactly the F statistic that we calculated above and exactly the p-value that we calculated above. So instead of just doing this whole slow procedure that we just did here to come up with a conclusion, you could just do an F test for coefficient significance. Run the regression, do test of experience equals 0, and you will have the test statistic and the p-value displayed here. So again, we would be concluding here that that the coefficient is significant. Note one important fact here is that the above is the t-test or f-test for the coefficient on experience being 0. But the t-test for the variable experience equals 0 is not what we want. So if we do here a t-test of experience equals 0, so that was test of experience equals 0. But here t-test of experience equals 0, it would give you a completely different thing than what we're trying to accomplish here. And this is, it's basically going to be mean 17 years. So this, how many years of experience a person has. And so if we're doing the t-test for this variable, well, the p-value is very high because this number is certainly significantly different from 0. So again, not what we're doing here. We're testing whether the coefficient on experience is equal to 0, not the variable. Okay, so next we're moving on to the f-test for joint coefficient significance. So this is actually what the f-test is really used for. So we're testing for a coefficient significance of several variables at the same time if they're jointly significantly different from 0. So here we would be having the null hypothesis would be to restrict these both of these coefficients on experience in tenure equal to 0. And here we have the restricted model. So you see that the experience and tenure are not included. And this is the unrestricted model where we have the experience and tenure and all the independent variables being included. So what's the difference from the previous example is that now we have two coefficients instead of one coefficient that we're testing for significance. But everything else is the same. So we estimate the restricted model, we save the sum of square residuals from it, we estimate the unrestricted model, we save the SSR for the unrestricted model using this E of residual sum of squares. And here Q is equal to 2 because we're testing two coefficients. We're generating the F statistic, which is again the difference between the sum of squares for residuals for the restricted and the unrestricted regression. And this is the sum of square residuals for the unrestricted model. And these are the degrees of freedom for numerator and denominator. So now we can display the F statistic here. So you can see this is the restricted model that we're seeing here. And that's the unrestricted model. And here we're calculating the F statistics. So now we have a much larger value of 42. The F critical value we are going to find again using the inverse F tail. with q degrees of freedom in the numerator and n minus k minus 1 degrees in the denominator, 0.05 probability in the upper tail. And so if we compare the F statistic to the F critical value, we see that the F statistic is larger, therefore we reject the null and the coefficients are jointly significant. We can also calculate the p-value for the f-test, and that will be f-tail, give the 2 degrees of freedom for the numerator, denominator, and the f-statistic, and then we can display that the p-value for the f-test is practically 0. So these coefficients are definitely jointly significant. So a much easier way to accomplish the same thing is just using the Stata command. So regression of wage on education, experience, tenure, and female. And then we put test, whether experience equals 0 and tenure equals 0. And if you remember these numbers for the F statistic of 42.86, and then the p-value, which is a very small number, these are the numbers that this test is giving you. So you can recognize the same test statistic, and that is the p-value, which is very small. So very easy to test, not just if this coefficient is significantly different from 0, and this one, if it's significantly different from 0. So individually, we know that they're significantly different from 0. And now we know that jointly, both of them, they're also significantly different from 0. Okay, the final test for coefficient significance, this is the overall significance of all of the regression. And so we would be testing if basically the regression model makes sense and it's well specified. So we would be putting all coefficients to be jointly significantly different from 0. So here we have, we're testing whether all of the coefficients are jointly significantly not significant or significantly different from 0. Here, the restricted model would be just having an intercept. And when we estimate it, I want you to note that this intercept that we calculate here is the same as the average of wage. So if we have regression of wage, this is the regression output. Notice that there are no independent variables here. We only have a constant. But if you summarize wage and you see what the mean for wage is, this number is exactly the same as this number because that's the intercept that we have here. Another very interesting thing that's happening with this regression is that the total variation in the model that we have, this is the total variation in the dependent variable wage, is the same as the residual, because if we don't have any independent variables, the model does not explain anything. So everything is a residual variation. So moving on, we are estimating again the restricted model, and storing the sum square residuals, and the unrestricted model. For the unrestricted model, if we do display E of F, that is storing basically the F statistic, and it's this number 74.40. If we look at the regression output, this is exactly this number here. So it's already being given to you. Let me take a minute and talk about this table here. And this table is called the ANOVA table. So here we have that the sum of squared for the model or explained, and sum squared for the residuals and total. These are the degrees of freedom. This is the number of independent variables, and this is n minus k minus 1. And this is n minus 1. So this is the number of observations minus 1. So the sum of the mean squares is the sum of squares divided by the degrees of freedom, and that is the mean square. And this is the mean square. So if you divide this number by this number, you will be getting this F statistic here. That's how this F statistic is calculated. And the p-value is again associated with this F statistic. So what this is showing here is that all of the coefficients are jointly significant. This means that you have a regression model that is well specified. So this is not surprising because look, all of the coefficients were individually significant if we look at their p-values, but they're also jointly significant, very significant if we look at the joint tests. Okay, so just to go through the exercise, we could be calculating the um, here we could be calculating the F statistic using the formula that we have. And so just remember this number here, 74.4. So here, if we calculate the F statistic as the difference in the sum of square residuals divided by this, we would be calculating exactly the same number. So we can do that by hand as well. And the one interesting fact is that we can actually calculate the F statistic using R squared in an alternative way. And this is just by using the R square here and 1 minus the R square here. And this is, again, the degrees of freedom in the numerator and denominator. That's actually the degrees of freedom in the model versus the residual. And if we display this F statistic 1, this is the same number as this one. And this is, again, because if you look here, the sum of square for the restricted model, this is actually the same as the sum of squares total for the unrestricted model. So once you plug in this value and you do the calculations here, this is how we get to this formula. So, okay, we calculated the F statistic. We can display the F critical value, and that's inverted F tail with q degrees of freedom in the numerator. This is the degrees of freedom in the denominator and 0.05 significance level. So here, because the F statistic that we have here is greater than the F critical value, we would conclude that the uh, coefficients are significant. If we're to calculate the p-value, we can do that with the f-tail, degrees of freedom for the numerator, denominator, and the f statistic. If we display the p-value, it's so small that it's listed as 0. And because it's less than 0.05, we have, again, coefficients are jointly significant. Using the Stata commands, we can also do the f-test for overall significance by estimating the regression and then putting all of the coefficients equal to 0. So here is putting all of the coefficients equal to 0. And so notice that these numbers here that we get for the F statistic and the p-value would be exactly the same as the F statistic and p-value here. Okay, and so this concludes the various f-tests. So again, for f-tests, we can test whether one coefficient is significantly different from 0, but we typically wouldn't do that because we can use a t-test. So it's best when we use two coefficients to test them if they're significantly different from 0. Um, and it's also used to test for the overall significance of the regression as well. Okay, finally we have the Lagrange multiplier test for coefficient significance. So this is a chi-square test for several coefficients to be jointly significantly different from 0. So it's doing similar things like the f-test, and it's also less used than the f-test. So how does this procedure work? First of all, we this is the unrestricted model that we have with all the independent variables. And if we want to test whether these two coefficients are equal to 0 or not equal to 0, so we can estimate the restricted model by excluding the experience and tenure from the model here. So we would be regressing the dependent variable on the restricted set of independent variables. So here we have wage on education and female. Our restrictions are equal to 2. And so after we estimate this restricted model, what we would be doing is we would get the residuals by just doing predict. We give it a name, e hat, comma, residuals is storing the residuals. So now, very interestingly, we will be regressing e hat, the residuals from this regression here, the restricted regression, on all of the deep independent variables. So think what just happened is that the residuals from this is all of the variation in wage that cannot be explained by education and female. So if this is all the regression in the dependent variable that cannot be explained by education and female, we want to see by how much these experience and tenure contribute to be, how much they contribute to being able to explain the dependent variable. So this is the LM statistic. It's equal to um, the number of observations times the R squared from this regression. So here we can display the number of observations and the R square and multiply them to get the LM statistic. So if we look at what the number of observations is, we can use E of n, and that's 526. So this is the number here for the number of observations. And display E R2 is the R squared. And so if you look at this number, that is this number, the R squared. So the LM statistic is the number of observations times the adjusted R squared. So here we have the LM test statistic is equal to 74.32. Okay, so we can calculate the critical value for the chi-square distribution, and this will be the inverse chi-square tail. This is the number of restrictions and 0.05 significance level. So here we have, this is the critical value. We compare that to the test statistic, and because if the test statistic is larger than the critical value, then we would reject the null and the coefficients are significant. So this is the case that we have here. Alternatively, we can calculate the p-value for the chi-square distribution. And here we have inverse, here we have the n chi-square 2 tail, and this is giving the degrees of freedom, telling it it's this is the significance level and that's the test statistic. And so this is the p-value, which is very small. It's less than 0.05, and therefore we would reject the null hypothesis and the coefficients would be significant. So here we're doing the same things with the Lagrange multiplier test for coefficient significance as with the F-test, but again, the F-test is more popular. So that concludes the regression inference or hypothesis testing in regression. Thank you for watching.